Here's an extra practice worksheet for linear algebra, math 2331. This worksheet covers some of the material in sections 5.2 and 5.3. So we get started. We are given a matrix A in number 1. We have 4 rows and 2 columns. We want to find the matrix of orthogonal projection onto the subspace, the image of A in R4. Well, what we need here, first, we need to find an orthonormal basis for the image of A. But you see, if I label this V1 and this one V2, note that V1 dotted with V2, we get 4 minus 4, which is 0. So I already have 2 orthogonal vectors whose span is the image of A. And the only thing I really need to do is just normalize them. So let's calculate the length of V1 and the length of V2. Both of these are square roots. For the length of V1, we get a square root of 4 plus 4 plus 1. This is 3. Square root of 9 is 3. For V2, we have 4 plus 16 plus 16. This is the square root of 36, which is 6. So my matrix with orthonormal columns, I will call this Q. And I just take each vector and divide by its length. So I have 2 over 3, 2 over 3, 1 over 3, and 0. And then when I take V2 and divide each entry by 6, I get 0. I have 1 over 3 minus 2 over 3 and 2 over 3. The matrix of projection that I'm looking for in this problem is QQ transpose. Now you notice every entry in my matrix has a 3 in the denominator. So let's just factor out a third. It can make my life just slightly simpler as I'm calculating this projection matrix. So then I have 2, 2, 1, 0. I have 0, 1, minus 2, and 2. There's matrix Q, and then Q transpose, well, we just interchange rows and columns. Will look like this. So the first column of Q becomes the first row of Q transpose. I have 2, 2, 1, 0. And then the second column of Q becomes the second row of Q transpose. This will be 0, 1, negative 2, and 2. So you notice this is a 4 by 4 matrix, as it should be, because this projection map will map R4 to R4. Now, I can pull out a 1 over 9 here, the 1/3 times 1/3. The nice thing when you're multiplying matrices is a constant like this, or like this, you can just factor all out in front. Well, first let's fill out the first row of QQ transpose. I can take this first row and dot it with each column. When I do, you see I get 4, 4, 2, 0. I have 4, 4, 2, 0. Now for the second row of QQ transpose, I take this second row and dot it with each column. So what do I get? You see I get 4, and then I have 4 plus 1, which is 5. Then we have 2 minus 2, which is 0. And then finally, we have 2. So this is the second row. We have 2 more. Now take the third row and dot with each column. You see, first I get 2 and then 0. 2, 0. Then the third entry, we have this dotted with this. We get 1 plus 4, which is 5. And then finally, I have negative 4. One more row. We take the bottom row and dot it with each column, but really what I do, I just get 2 times this bottom row. So this will be 0, 2, negative 4, and 4. Now, we notice this is symmetric, as it should be, because it's QQ transpose for some matrix Q, but that is sort of a sanity check you can do. If you are calculating the matrix of projection and you don't get a symmetric matrix, then probably you've made a mistake somewhere. This is my final answer. It's also perfectly fine to leave the 1 over 9 out in front. Number 2, we're trying to generate examples of certain linear transformations, which are not orthogonal transformations, but satisfy certain things. And it's enough to just write down the matrix. So in 2A, we want to map from R2 to R2 that preserves angles, but is not an orthogonal transformation. In 2B, we want a linear transformation such that T of E1 and T of E2 are unit, but again, not an orthogonal transformation. So thinking about 2A first, if we go back to, say, section 2.2, we had reflections and rotations, and those preserve angles, but those are orthogonal transformations. We also, though, had scaling. Here, all you do is change its length, but you do not change direction. So that's what we're going to use here. We will use a scaling transformation. The lengths are changed, which means it would not be an orthogonal transformation, but the angle between, say, T of X and T of Y would be the same as the angle between X and Y. So an example of this, we can just take scaling by 4, something like this. And looking at the matrix side, well, the columns are not unit, so it is not an orthogonal matrix. As I mentioned, these columns are not unit, so without a doubt, this does not correspond to an orthogonal transformation. Now, part B, T of E1, T of E2 unit vectors. Whatever I write down, these columns will be unit, but it doesn't say that the angle between T of E1 and T of E2 needs to be a right angle. That's the key to this one. So I can map E1 to E1. I can map E2 to minus E1. Here, the columns are definitely unit, but my note would be that the columns of this matrix are not perpendicular. So this matrix corresponds to a linear transformation from R2 to R2 such that T of E1 and T of E2 are unit, definitely not an orthogonal transformation. In fact, this matrix is not invertible. This was number 2. Number 3, we have QR factorization. We will have work to do with this problem. So let's label V1, V2, V3, and we begin the process of Gram-Schmidt. The first step, we take V1 and divide by its length. With the length of V1, we have a square root of 2, 1 plus 1, underneath the square root. So my first unit vector, which will be the first column of matrix Q, I just take V1 divided by its length. So this will be 1 over the square root of 2, 0, and 1 over the square root of 2. Now you can go ahead and highlight this because that will be an entry in my matrix R. Next step, we need the next direction. So this, the component of V2, which is perpendicular to the line spanned by U1, would be V2 minus V2 dotted with U1 times vector U1. We can write what this is. V2 is vector 1, 1, 1. And then we will have a dot product here. It will be something over the square root of 2. There's a minus sign. We just get 2. 1 plus 1. So this is the next number right here, which if you want to simplify, it's fine. You could multiply by square root 2 over square root 2. This is just the square root of 2. But this is my next number in my matrix R. Well, what happens when I subtract? We get this vector. It's just E2, in fact, but we get the vector 0, 1, 0. And then you notice this length is 1. So I have another entry in my matrix R, but also I'll just go ahead and write U2 over here. I take this already unit vector and you can just divide by the length 1, but this is U2. Now, third direction, this would be the component of V3, which is perpendicular to the plane spanned by V1 and V2, or equivalently, the plane spanned by U1 and U2. We take V3 minus, we have V3 dotted with U1 times vector U1, And then minus, we have V3 dotted with U2 times vector U2. This gives me my third direction. So there I have filled in U1 and U2. V3 is the vector 1, 3, 0. And then I will subtract off. I need to calculate this dot product and this dot product. V3 dotted with U1. Well, it's here and here. You notice I just get 1 divided by the square root of 2. This is 1 divided by the square root of 2. Then we take V3 dotted with U2. You notice I get 3. So these two numbers, this one and this one, these appear in my matrix. Maybe I will just make a comment. You see 1 over square root 2 is square root 2 over 2. This is square root 2 divided by 2. Now, maybe I will simplify this before I add because it's a lot to look at like this. This first vector is 1, 3, 0. And then the next vector, you see what happens when I multiply through, I just get a half, 0, a half. So this is a half, 0, a half. And then I subtract off this third vector, which is 0, 3, 0. So that makes it a lot more simple to work with. So what do I get here? Well, I have 1 minus a half, which is 1/2. I have 3 minus 3, which is 0. And then I have negative a half for my third one. Okay. So this is my third direction, but it's not yet unit. The length of this vector, well, it's the square root of a fourth plus a fourth, which we get, this is 1 over the square root of 2. It's the square root of 1/2, which is 1 over the square root of 2. Or just like above, I can write this as square root 2 over 2. It's okay to leave square roots in the denominator, but I'll leave it like this. So my final unit vector, I take this vector and I divide every entry by square root 2 over 2. I will get 1 over square root 2, 0, and negative 1 over the square root of 2. So let me highlight this one. This was our last entry of matrix R. At this point, we have done the entire Gram-Schmidt process on these 3 vectors. And over here, these are the columns of my matrix Q. And then I can fill in the entries of matrix R just by looking at everything I've highlighted. So let's write them down. Q has columns 1 over the square root of 2, 0, 1 over square root 2, then 0, 1, 0. Then we have 1 over square root 2, 0, negative 1 over square root 2. Now check. If you think you have a matrix Q, but the columns are not unit, or if the columns are not perpendicular, you have made a mistake. But we see here, columns are all pairwise perpendicular and unit. Fantastic. Now for matrix R, well, we can fill it out just looking at all of this work, column by column. So the first column you see will be square root 2, that's here, and then 0, 0. Square root 2, 0, 0. Now the second column is here. It's square root 2, 1, 0. The third column I get from the numbers when I created the vector U3. So I have square root 2 over 2, 3, square root 2 over 2. This is my matrix R. And this ends this problem. We have found matrix Q and we have found matrix R. This was a great question. Number 4. We are given S is an orthogonal n by n matrix. A is a symmetric n by n matrix. we want to show S inverse AS is symmetric. Well, the first thing to observe is here, because we have an orthogonal matrix, this means S inverse is S transpose. So let's write this as a note. S inverse equals S transpose. And so what this means for us is that this matrix, S inverse AS, this equals S transpose AS. That is really going to help us out. Now I just need to show S transpose AS is symmetric, given that A is symmetric. How we do this? Well, S transpose AS transpose. We want to see when we do this, do we get this matrix back again? If the answer is yes, then we have a symmetric matrix. If the answer is no, then we would not. But here, the answer should be yes, because I'm supposed to show this is symmetric. Well, we have a product of matrices. When you take the transpose of a product, it goes in the other order. So this would be S transpose, A transpose, S transpose, transpose, like this. Well, A is symmetric. This I'll recopy. A is symmetric. And then S transpose, transpose, well, you interchange rows and columns, and then you interchange them back. We have matrix S. Okay, that does it. So this is the end of our extra practice worksheet. Thank you so much, students. Have a wonderful day.